All right, so let's move on to the fifth and final part of the course, which is going to have a fairly different flavor than the first four. But it's, I mean, one thing in common with the last several parts is that there's been very exciting progress just in the last couple of years. So again, really emphasis on sort of recent breakthroughs. And so the main change is I'm going to switch from welfare maximization to revenue maximization. Okay, so sum over the payments rather than the sum over the values. Okay, so literally for 17 straight lectures, we've been talking just about welfare maximization. Okay, so we're going to have 3 lectures where we talk about revenue maximization instead. So if you like, you can think about this, we're switching from the perspective of something like a government, trying to allocate resources like spectrum licenses in an efficient way, to, you know, more of a monopolist who just wants to make a lot of money. Or you want to think about it, we can be switching from a competitive market where you can't really get away with monopoly pricing to a less competitive market where you can. And I want to open the lecture just by reminding you of some stuff from last quarter about the challenges of revenue maximization that don't come up when you're doing welfare maximization. So one reason we talk a lot about welfare is just because it's a fundamental objective. It's well motivated in many settings. Many real-world combinatorial auction designs are really motivated by welfare concerns. But the second reason is that it's just, I mean, it's pedagogical. So welfare is just sort of much easier to study. So you have like so if you don't care about computation, you have the VCG mechanism, which says you get incentives for free for welfare maximization. There's a mechanism which maximizes welfare even ex post, as well as if you knew the valuations up front. Okay, so there's literally like zero loss from not knowing valuations up front if you want to do welfare maximization, if you don't care about computational issues. Okay, and the story is very different with revenue. It's actually much more sort of exasperating to study because there's no analog of the VCG mechanism at all. So which mechanism makes the most revenue just depends on the input. And general mechanism A will be better on some inputs than mechanism B. Even if there's just sort of one buyer and you're just trying to figure out what take it or leave it offer to make them, right? Or, you know, how to set a reserve price on eBay. Should I set it to $10 or $20? Well, it depends. Right? So basically you're hoping there's going to be valuations just a tiny bit above your reserve price, but if it's just a tiny bit below your reserve price, you're out of luck. Okay, it was a bad reserve price. So as a result, let me remind you that even just to start reasoning and talking about optimal revenue maximizing mechanisms, the most common way to even, you know, start the discussion is to assume a prior. And then when you have a prior, you can compare the performance of 2 different mechanisms just through their expected revenue. Okay. And this was the reason that we did talk about prior distributions last quarter in 364A. Now we're sort of used to them because we've been talking about Bayes-Nash equilibria in simple auctions. We talked a little bit about Bayesian and set-compatible mechanisms. So we've talked a lot about Bayes-Nash equilibria. Last quarter, we never talked about Bayes-Nash equilibria, basically not once. But we did have a prior for a couple lectures, and the reason was just because even though we were still just doing dominance strategy and center-compatible mechanism design, we just did it to compare the expected revenue of different auctions. Okay, so when we did Morrisons Theory, when we did the Buell-Klemperer theorem, this is why we had a prior. Now, for these few lectures, we are going to be studying not just DSIG mechanisms, we'll be studying Bayesian and center-compatible mechanisms. So we'll use the prior for, you know, in 2 senses. 1, to measure performance, but also 2, to, you know, reason about how bidders behave. Okay, so last quarter, it actually wasn't important that bidders even knew the prior. They had dominant strategies. Here for Bayes-Nash equilibria, it is of course going to be important that everybody knows the prior. Okay, so people do know that they're doing a best response on average over the actions of the other players. Okay, so really simple example. So we talked about one buyer. So again, I want to say a couple quick, you know, refresher on the single parameter setting, really very brief, just like 5 minutes. So when you just have one buyer, So if you have one buyer, I should say also, dominant strategy, incentive compatibility, and Bayesian incentive compatibility coincide with one buyer, right? There's no one else to average over. Okay, so it's just, it's the best to do direct revelation. And for one buyer, there's not much you can do. Okay, as a mechanism designer, you can offer you can make a take it or leave it offer. If you want, you can randomize. You could have a distribution over take it or leave it offers. Okay, so distributions over, so also called posted prices. Okay. And given a prior distribution capital F on the buyer's valuation, just assume there's sort of one good, single parameter, then of course, it's kind of obvious what you should do. You just say, well, if I set a price of capital R, I'll make R dollars whenever there's a sale. And then the probability of a sale is just the probability that the bidder's valuation is at least the offer that I make it. So 1 minus the prior capital F at the price that I offer. And I just want to pick the best one. Okay. And that's it. So there's nothing hard for one buyer and one good. And let me just remind you the punchline of Myerson's optimal auction theory. So if you have multiple buyers, and let's say one good for now, so the optimal single item auction, when you have valuations VI drawn from known prior distributions FI, and these should be independent, not necessarily identical, then the optimal thing to do is you give the item to the bidder with the highest what? Who remembers from last quarter? Anybody?
Virtual value.
Excellent. Gives item. If I was feeling mean, I would say, what's the formula for that again? But yes, there will be a Z. Gives item to the bidder with the highest virtual value, which is Z minus 1 minus the CDF at Z over the density at Z. Okay. So for example, if it's the uniform distribution, then this is just 2Z minus 1. Okay, so it would be minus 1 at 0 and 1 at 1 for the uniform distribution. So remember, virtual values can be negative. Okay, they can be negative or positive. So anyways, there's some formula for it. Actually, a couple caveats. This isn't, let me just tell you the fine print. So what I just said assumes that the phi i's are increasing. That's the only case we dealt with last quarter, and encompasses many of the distributions you'd ever care about. So Myerson called this the regular case. The theory extends equally well beyond regular distributions. There's just extra technical details that we're not going to focus on. We didn't focus on last quarter, and we're not going to this quarter either. So it assumes that. And then there's also the possibility, given that one virtual value could be negative, like this 2z minus 1 function, it might be that all of the bidders have negative virtual values, and in that case, you don't award it at all. Okay? And remember, this is a fundamental difference between welfare maximization and revenue maximization. Revenue maximization, it can definitely pay off to just leave stuff on the table. Okay? So if all phi vi's negative, no sale. Okay? And in the case of where all of the valuations are IID, so what I just said here is true as long as the distributions are independent, but they can be arbitrarily different distributions. If they happen to be identical distributions, then this becomes very simple. Then, if everybody has the same distribution, everybody has the same virtual valuation function. So if that distribution is regular, meaning phi is strictly increasing, then the bidder with the highest virtual value is exactly the same as the bidder with the highest value, or the highest bid. Okay? So if all the fees are the same, and we're in the regular case, then what this is telling you to do is to award it to the highest bidder. Well, except in the case where they're all negative virtual values, in which case you award it to nobody. So that just corresponds to awarding it to the highest bidder and supplementing it with a reserve price, where the reserve price corresponds to the inverse virtual value of 0. Okay? So summarizing, for the IID regular case, the optimal auction is nothing more than a second price auction with a reserve. Okay? Or if you like, an eBay auction with a suitable opening bid. Okay? So that's some nice stuff you get in the single parameter case. And in general, so that was specializing this, but now sort of actually generalizing this. And this was the version that we proved last quarter. So in general, even if it's not a single item auction, even if you have some more complicated set of feasibility constraints, what Morrisons Theorem tells you is that maximizing expected revenue boils down, i.e. is exactly the same problem as maximizing the expected virtual welfare. Okay, so that's how you solve it, and very generally in single parameter settings. So maximizing expected revenue reduces to maximizing expected virtual welfare, meaning the sum of the phi of VIs over the bidders that win. Okay. All right, so any questions? I hope this sort of jogs stuff that is you vaguely remember. Okay, so we're actually not going to really need to know the details of any of this. This is more just to set the context. The plan for this lecture, so like I said, there's been some very recent progress, but the plan for this lecture is more just to kind of do the setup and understand the issues better, okay? So no worries if you don't understand the exact details of what we talked about last quarter. So why is this interesting? The fact that maximizing expected revenue reduces to maximizing virtual welfare? Well, the first reason it's interesting is just conceptual. I mean, there's a zillion mechanisms you could run, and this gives us some kind of understanding about which one is optimal. Okay, so this is a reasonably crisp characterization of what optimal auctions look like. And we get some immediate interesting corollaries that are kind of unexpected from this statement. So in Morrisons Theorem, the feasible region is actually super rich. Okay, so say it's even just a single item auction for concreteness. Bidders have these different distributions. Maybe there's lots of bidders. You can do whatever you want. Okay, so you've got to be incentive compatible, but actually not even DSIC. All I insist is that you're Bayesian incentive compatible, and you can be randomized if you want. Okay. Well, Morrisons Theorem tells you, well, what you should do is maximize expected virtual welfare. Okay. And that's dominant strategy incentive compatible. This is again assuming, all of this is, I'm going to assume regularity. So it's dominant strategy incentive compatible because the allocation rule is monotone. You proved this on an exercise set last quarter. Welfare maximization gives you monotone allocation rule, so it gives you a DSIC mechanism. And it's also deterministic. Right? The values show up, you just compute the phi of VIs, and you just pick the best one. No randomization needed. So I allow you to be BIC instead of DSIC. I allow you to be randomized instead of deterministic. You're like, nah. No need. Okay? Optimal mechanism is neither. Okay? So the optimal BIC mechanism is DSIC and, assuming regularity, deterministic. Now, full disclosure, we didn't actually prove this statement last quarter because I never actually defined Bayesian incentive compatible mechanisms. So we only proved this for the feasible region of DSIC mechanisms, but basically the same proof works over the bigger feasible region of BIC mechanisms. Okay? So we proved it in spirit last quarter, even if we didn't prove it in letter. Okay. So that's reason number one to care about this reduction from revenue maximization to virtual welfare maximization. Conceptual, we know what optimal auctions look like. The second reason we might care is computational. So suppose you wanted to implement a revenue maximizing mechanism computationally efficiently. What this statement says is, well, if you can maximize welfare efficiency and efficiently, and you may or may not be able to, depending on the setting. We've seen plenty of examples, even single parameter settings, where it's NP hard to maximize welfare. But if you have an algorithm which maximizes welfare, then you can just reuse that exact same algorithm as a black box and maximize revenue. Okay, which is kind of amazing, actually, because these are totally different objectives, welfare, revenue. I just opened this lecture by saying how much more of a pain revenue is than welfare, and yet once you pass to just having a prior, independent valuations, computationally they become exactly the same. Okay, give me a black box for welfare, I'll just compute the fees, shove those in as effective valuations, and run the black box, and I'm done. I get a revenue maximizing auction. So both of those are very cool. So the goal then, for the remaining lectures of the course, so that was all single parameter stuff, right? Monotone allocation rules, that's not defined, obviously defined beyond single parameter. So what we want to understand is, to what extent can this amazing theory have a multi-parameter analog? And remember, multi-parameter is absolutely everything we've discussed so far this quarter, pretty much, okay? So for example, in combinatorial auctions. Okay. So to the extent possible, we'd like a multi-parameter analog of Meyerson's optimal auction theory. Now, Meyerson's optimal auction theory is from 1981, so that's 33 years now. But kind of shockingly, there's been some important developments just over the past few years. And again, perhaps surprisingly, some of those developments have been coming from computer science, not from economics. So today I mostly just want to help you understand the issues, do a little bit of setup, and then next week we'll sink our teeth into some of these recent results, and we'll see how far we get in the remaining lectures. Okay, but certainly I'll certainly be able to give you a flavor for the kinds of developments that have been happening just in the past couple of years. Okay. All right, good. So any questions about that before? So this is a review of challenges for revenue even in the single parameter world. Now I want to start contrasting this with the significantly more complex multi-parameter world. So any questions before we do that? Okay. So I'll be able to convince you that the multi-parameter world is very different, even just in the case of a single buyer. Okay? So warm up. One buyer. So multi-parameter here, the simplest way to make it multi-parameter is I'll just say there's two goods. Okay? Different ones, say. So there's going to be a prior over valuations. So I need to kind of say what the valuation should be. The simplest valuations I can think of are additive valuations. So let's talk about additive valuations. That means there's going to be a V1 and a V2. Let's even let them be IID. Okay? Let's try to start with something trivial. Okay, so the sum distribution capital F, V1 and V2 are IID draws, and the buyer's valuation for the goods it gets are just additive. So it gets both, it's V1 plus V2, etc. Okay. So now let's ask the same question we asked in the single good, single parameter world. Right, so again, there's no need to distinguish between BIC and DSIC. Right, that's not the issue here. Really, with one buyer, it's more like a pricing problem. Okay, so you can think of the mechanism design problem in the degenerate case of a single player as just we write down some options. We just kind of figure out prices to offer for the goods for sale. And with an additive valuation, it kind of seems like this is silly, right? So we've talked about additive valuations. Everything always decouples over the items. You can just handle the different items separately. So presumably what we should do is just kind of, there's some optimal price. There's like the same monopoly price for this distribution F. We'll just slap that onto the first good. We'll slap that onto the second good. And then the bidder can pick any combination it wants. Okay? So, all right, so what's like the simplest prior that's non-trivial? Let's say F is 1 or 2 with 50-50 probability. Okay? It's a pretty simple prior. So let's just think about item number 1. So if this is the distribution, what's the monopoly price? Monopoly price just means the thing that maximizes expected revenue. Okay, so there's an item, the person either has value 1 and the person has value 2. How should we price that? Suppose there were only one item in the world. What should we do? So a price of 1 would get us what expected revenue? 1, right? They'll always take it, we'll get a buck. A price of 2 would get us what expected revenue? 1, because we'll get 2, but only half the time. So it doesn't matter, okay? So 1 or 2, whatever. We get expected revenue 1, okay? So there's 2 goods, so we get expected revenue 2, okay? All right, so so if we wanted to kind of explore the design space, so what else could we do? Well, I guess if we wanted, we could only sell the goods as a package, right? So we could say, look, this is an incentive compatible mechanism. Either you get neither or you get both, and if you want both, you have to pay some amount, maybe like 3. I mean, that's certainly an incentive compatible mechanism, right? I make it a take it or leave it offer just on a bundle. Okay, so how well does that do? Worse? What does it get?
It's like 1/4 chance of getting 1.
If I bundle them together for a price of 3?
I think, isn't it just half chance of getting, sorry, no, don't worry.
Why would you ever get, so sorry, say it again?
You've 1/4 chance if they're both valued at 2.
Yeah.
Make 1.
It's from the seller perspective, right? We're not talking about utility, right? So we want to do revenue.
Shouldn't it be a 3/4 chance of making 3 because 3/4 because they have to value either of the items at 2.
Right. So the only way the person won't take it at a price of 3 is if it's 1 for both. And so that's probably 1/4. So the probably of a sale is 3/4, and you make $3. So that's 2 1/4, which is actually better, right? So that's interesting. So better, bundle at price 3, expected revenue is 9/4. So, okay, so we need to work on our intuition a little bit better maybe. Right, we're so used to welfare, where it's true. When you're maximizing welfare, additive evaluations, it does trivialize things. It really does decouple over the items for welfare, okay? That's the correct intuition. The incorrect intuition is thinking that, lessons for welfare carry over to revenue maximization. Sometimes they do, but I mean, it's kind of an amazing theorem when techniques for welfare carry over. Okay, that's sort of the exception that proves the rule. So even in like the simplest multi-parameter thing we could think of, it's not like the optimal auction is not simple or anything. This is the optimal auction, I'm pretty sure, but it's maybe not the first thing we would have guessed. Okay, so let's look at another example. Let's say f is 0 or 1 or 2, equally likely. Oh yeah, one thing I should say is the error in the reasoning actually is really easy to see if you think about like a really large number of goods. Right, so imagine you have one buyer, m goods, IID going to infinity. Right? The law of large numbers says that the bidder's value for all of the goods gets highly concentrated as the number of goods grows large. So you know almost deterministically what the person's willing to pay for the grand bundle. So why not just price the grand bundle at slightly less than its expectation? And you'll extract almost of the full welfare almost all of the time. Okay? So it shows up already with 2 items, but the power, bundling for additive valuations, the intuition is very clear when you think about a large number of items. Okay, so good. So let's think about this example. 0 or 1 or 2, equally likely. So what are the things we've tried? So if we sell separately, I cannot spell that word. Individually. So what's the monopoly price on a single item with this distribution? Price 1, price 2, doesn't matter.
1, 2 the same, right?
Doesn't matter. 2/3 either way. Right? Either you can get $1 with 2/3 probability or $2 with 1/3 probability from a single item. Okay? So at price 1 or 2, expected revenue from the both is 4/3. So bundling, okay, so given that this is 4/3, a price of 0 is uninteresting, a price of 1 is uninteresting, because that would be less than this even if you always sold it. A price of 4 seems a little aggressive, because you're only going to sell with probably 1/9 if you price it at 4. So that leaves 2 and 3. So a price of, if you set it at 3, then the only way you'll sell it at 3 is if you have at least 1, 2, and at least one thing that's at least 1, right? So the winning combinations at a price 3 are 1, 2, 2, 1, and 2, 2. So it's a 1 in 3 chance of getting a price of 3. So that's expected revenue 1. Price 2, so when will the bidder take it at price 2? Well, as long as it's not 0, 0, 0, 1, or 1, 0. So now there's 6 outcomes will take it. So that's a 2/3 probability, price 2, so that also gives you 4/3. Okay? So bundling, again, at price 2, expected rev equals 4/3. Okay? So there's something better than either of these. So it's better to offer to the bidder. So with one bidder, you can basically think of it as, I just write down a bunch of options, right? So I basically say, you can pay this and get this. You can pay this and get this. You can pay this and get this. And then the bidder just walks up and say, that's my favorite option. Okay, that's a way you can think about mechanisms when there's only one buyer. And so the options are basically, we say to the buyer, you can take any one item, so either the first item or the second item, at a price of 2, or we'll give you both at a discount, price of 3. Okay, and so again, so there's 3 options. The buyer picks their favorite, whichever one maximizes their utility. Okay, so again, it's instead of compatible auction because, in effect, whenever the buyer can make any decision they make, it translates through the revelation principle to an incentive compatible auction. Okay. All right, so why? Okay, I claim this is better than 4/3. Let's see why. So this is just the valuation profile. So V1 is 0, 1, or 2. V2 is 0, 1, or 2. Each of these is a 1/9 chance of happening. All right, and so really, okay, there's an issue of tie breaking. So assume that the buyer always breaks ties in favor of the seller. And the way you can enforce that is just you add little epsilons. Okay, so think of this as really price 2 minus epsilon, and think of this as price 3 minus 2 epsilon. Okay? All right, so everything costs at least 2. So clearly we're getting a 0 in all of these, right? How about here? So if both valuations are 1, how much money do we get? 0. How about if it wants 1 for 2 and the other for 0? Yeah, so then it'll take the item it wants. Okay, again, that's why I made the price 2 minus epsilon, to make sure it really takes it. Okay, so how about, all right, so another probably easy one. How about 2 and 2? Yeah, then it's going to take the grand bundle, right? How about here? How about if one's 2 and one's 1? Yeah, so this is why I did the minus 2 epsilon, right? So here, if it's 2 and 1, its value for the grand bundle is 3. Its value for just the better item is 2. Utility is epsilon if it takes the one item, and the utility is 2 epsilon if it takes the grand bundle. So it takes the grand bundle. 3, 3. Okay? So the expected revenue well, so 3/9 it gets a 3. 2/9 it gets a 2, aka 13/9, the relevant point being it's bigger than 12/9, which is what we were getting with the other options. Okay? All right. So not totally clear what to draw from these examples yet. But let me, this example I won't do all the details, but I'll tell you the example. It's basically the similar complexity, which shows that this corollary is already false with two items, one buyer. Yeah, that's it. So it's no longer to be true that optimal mechanisms are necessarily deterministic. Okay? And so this will give us already a bona fide separation between the two scenarios. So example, again, IID. 1, 2, or 4 with probability 1/6, 1/2, and 1/3. Okay. So I write it down. No tricks up my sleeve. And the claim is that the unique optimal auction is the following. It's similar to this one, the twist being you offer any one item with probability 50% at a price of 1. What do I mean by that? I mean that one of the things, one of your options, is to buy a lottery ticket, okay? And it says its price is $1, and it's a lottery ticket that gets realized as item A, the first item, with 50% probability. And 50% probability gets realized as nothing. Okay? Bidders are risk neutral. All right? So you pay $1 with certainty, and then after you go home and open the box, 50-50 chance that it has item A. So that's what I mean by I'm selling 50% probability version of item A. And so you have the option for either of the two goods, or both items with probability 100% at a price of 4. Okay? So I'll leave as an exercise. So that first of all, so part A, the expected revenue of the auction I just told you is a little less than 3.5. And B, that all deterministic auctions are strictly worse. Okay? Where deterministic auction just means that the only outcomes are either you get nothing, you get item 1, you get item 2, or you get items 1 and 2. Okay? Those are the only 4 possible outcomes in a deterministic auction with 2 goods. Okay? And this auction has an outcome that does not look like that. Okay? You might wonder why not just, offer it with probability 100% at price 2. But it's really not the same thing. Okay? So when you charge an extra $1 for an item, you subtract 1 from a bidder's utility. Okay? When they have it. Okay? They pay $1 more, utility's 1 less. When you allocate it with 50% probability, that's like dividing their valuation in 2, whatever it may be. Okay? So the probability is a way to manipulate the utility in a multiplicative way. The price manipulates the utility in an additive way. And you just can't really simulate one with the other. Okay? But again, this is really something you should play around with to explore, and not really to do here in class. All right? Okay, so what was the point of all this? Well, one was just, so we're back in the revenue maximization mindset a little bit. But also, this kind of, remember we have this motivating goal, develop a multiparameter analog of Morrisons theory. So this sort of tells us to brace ourselves a little bit. Right? So this tells us that more complicated things are going on very quickly as soon as you move to multi-parameter settings. All right? So we should maybe limit what kind of analog we could hope could be true. And we should maybe be ready to use relatively sophisticated techniques to derive whatever multi-parameter analog exists. Okay? So upshot. Okay, so first of all, notice how much was the same in all of these examples. There was always one buyer, there was always two items, there was always an additive valuation, and V1 and V2 were always drawn IID. The only thing that varied was capital F, and we weren't really varying it that much. But the format of the optimal auction was varying significantly with these small variations in capital F. And this is even with one buyer. Okay? So look at how different that is from the single buyer, single good case, where always what we want to do is some take it or leave it offer. And the only thing that can change is exactly what that numerical value is, which changes in some easily understood way as you vary the prior f. Okay? It's just whatever the maximizer of that r times 1 minus f of r is. Okay? So the format of the optimal mechanism varies with f. So even n equals m, n equals 1, m equals 2, IID, additive. And what this example shows is that the optimal auction might be randomized. And so this immediately tells us that there's not an analog of Morrisons theory of the form, take as input the valuations, do some deterministic transformation, and then run welfare maximization, and out pops the optimal auction. We now know that is false. Okay, we now know there cannot be an extension of that form. All right? Okay. So any questions? Okay. All right, so how can we get a handle on these optimal mechanisms? It seems like we might need, sort of explicit closed form formulas seem kind of hopeless. So we need some more general powerful tool. So where we're going to mostly explore optimal auction design is through linear programming. Okay, and so I want to just say a few simple things about using linear programs to characterize optimal auctions today, and then I'm going to say some less simple things next week. Good. All right, so here's the first observation, which is rarely directly useful in its own right, but this is a good starting point. I claim we can formulate the optimal mechanism as the solution to a linear program. And we're going to start with just the single buyer case, but actually this will be general enough it'll extend to bona fide mechanism design, so with multiple bidders. Okay? So, this is not very explicit, just writing down some linear program whose optimal solution is the optimal mechanism, but it's a start. We've got to start somewhere. Okay? So for starters, let's just say one buyer. I am going to allow any number of items. There's no reason not to here. So set U of m items. I'm going to assume that the prior distribution has finite support, just like in the examples. So there's a finite number of different valuations the bidder might have. So there's a finite set capital V. I'm also going to assume additive valuations. We'll probably be able to talk some about generalizing that, but additive valuations will be interesting enough to get started. And then we know the prior. So we're just told a probability mass F of VL, or f of V, for all V and V. Okay? So these are all non-negative numbers summing to 1. Okay? Oh yeah. Also, what I'm going to say for the rest of the lecture, so remember each of these is really an M vector. It's an additive evaluation. There's M items, so it's how much you value each of the M items. We'll never need to assume that these are independent. Okay, so these can be arbitrarily correlated. There's only one buyer, so we're not talking about correlation between different bidders. There's no other bidders right now. But between items, the relevant parts of the additive evaluation can be correlated. All right. So the LP, excuse me, the decision variables are as follows. Or I should say, so the revelation principle, as usual, applies. So at least in principle, in the search for optimal mechanisms, we can focus on those where direct revelation is a dominant strategy for the bidders. Again, one buyer, so it may as well be dominant strategy. Okay. So the decision variables are just xjv. So this is the probability that buyer gets item J when it reports the valuation V. And P of V is just the payment, okay, or expected payment. Remember, we're thinking of buyers as being risk neutral, so we really don't care. If the mechanism is randomized, all we really care about is the expected payment. Okay, so we'll just keep track of the expected payments. Okay? So in a deterministic mechanism, for example, these are going to be either 0 or 1. Okay, so the first two examples, these would be 0 or 1. In this example here, this corresponds to having an xjv equal to 0.5. Okay? Okay. So those are our decision variables. And the observation is that it's easy to write both the revenue and the incentive compatibility constraints, and also individual rationality constraints as linear objective and linear constraints in these variables. Okay, so I'll show that to you, but that's the point here. Okay. All right, so the objective. All right, so this is what we're solving for. Okay, so we think of this as defining a mechanism. Okay. All right. And so now over the space of all mechanisms as represented by these xj's and p's, which one's the best? Well, so we want to maximize revenue. And so we want to maximize the revenue from this one buyer. And so assuming that it actually does do direct revelation. So we just say, well, what are all of the valuations that the buyer might have? What's the probability that it has a given valuation? And then how much money do we get from the buyer when its valuation is V? Okay? So that's the expected revenue. Remember the F's, little f's are given. The P's are variables. That's a linear objective. Okay, so the constraints. So let's start with the IC constraints. So these are for all V and V prime. So I'm thinking here of V as the true valuation and V prime as a potential misreport. So what's the utility of a bidder when its true valuation is V and it actually reports V? So that's just going to be, well, it's sum over the items. It's the bidder's true value for the item. The probability it gets that item when it reports truthfully, the payment it gets when it reports truthfully, and that should be at least the same quantity. Again, true valuations, but now it looks at the new allocation probabilities with the misreport and the new payment with the misreport. Okay? So these are the IC constraints. Whatever your true type V is, you get better utility from reporting it than from any alternative type V prime. So the individual rationality constraints, this is what says that a directly revealing bidder should always get non-negative utility. So this is just basically, this should be non-negative, okay? So for all little v and big V, if I look at the utility when it reports truthfully, that's non-negative, okay? And also, of course, you want these, these things are supposed to be probabilities. So let's make them so. Okay. So this is a linear program in the decision variables x and p. Okay. Because again, we know the potential valuations and we know the distribution little f. Agreed? Linear program? And the claim is that the feasible solutions to this linear program correspond exactly to the IC and IR mechanisms, and that the objective function faithfully models their revenue, right? So if you give me a mechanism, what is it? It's by definition, a mechanism is an allocation rule and a payment rule. And so the allocation rule of your mechanism, I can pretty much just read off the values of the XJVs and the PVs. I imagine feeding it a given input V, and I just watch what it does. And if it flips coins, that just tells me the probabilities, these XJ of Vs. Okay, so given a mechanism, that induces a feasible solution. Given a feasible solution, it induces a mechanism, right? So again, basically on a given report V, a solution to this linear program just tells me exactly what to do. Okay, it tells me with what probability to give a given item J to the bidder. Okay. Because valuations are additive and we assume bidders are risk neutral, I can treat items independently, right? So if X1 is 0.2 and X2 is 0.5, I can just flip independent coins for deciding whether to give the buyer item 1 or item 2. Doesn't matter, okay? So if you agree, then just identifying the optimal mechanism, the revenue maximizing mechanism with respect to a given prior, boils down to just solving this linear program. Agreed? Okay. All right, so some more comments. So as we noted, so deterministic mechanisms are the special case where each xj of v would either be equal to 0 or equal to 1. But as we know, optimal mechanisms might not have that property, so this need not be integral, this polytope. What else? Right, so for example, how would the grand bundle, so how would bundling all items together be represented as a feasible mechanism? That would just say for a given v, either xjv is equal to 0 for all j, or xjv is equal to 1 for all j. Okay, so that would be equivalent to the mechanism that all it does is offer the grand bundle at a common price. And then for v's below that bundle, all the xjv's would be 0. For v's above that price, all the xjv's would be equal to 1. Okay? So the size, and this will become important in a second. So the size, well, we have one decision variable. So how is it scaling? So basically for each choice of j and each choice of v, we have a decision variable. We're not so bummed about having a decision variable for each item j. That seems reasonable. Having one for each possible valuation is kind of a lot, potentially. There's a lot of potentially different valuations. But it's also, hard to see how you'd write down a linear program that didn't have that size, that encoded incentive compatibility constraints. Okay? So size, poly in V. All right? So that's how you should think of the size of this linear program. Okay. Now, one thing that's nice about the linear programming approach is it can be extended in lots of different ways. Okay, and for now, let me just mention that it's easy to extend this to multiple buyers. Okay? So So now we're going to have variables x, I, j, v. All right? So again, now we have n buyers, each with an additive valuation drawn from some known prior. Okay? So now instead of just a valuation of a single bidder, we have a valuation profile. So this is an n vector. And so now we specify the probability that bidder I gets item j when the valuation profile is whatever it is. Okay? And we again keep track of the expected payment or the payment by bidder I. And now it's not just for a single report by that bidder I, but it's by the full valuation profile V. Okay? So again, this is just encoding the allocation rule and the payment rule now that we have multiple buyers. And so now the new LP. All right, so now we're just going to sum right, so this is everything that might happen, every valuation profile, the probability of that valuation profile, and we just look at the amount of money we get from each bidder. Okay? So that's the revenue with multiple buyers. And now, so one thing I want to point out is now that we have multiple buyers, there's suddenly a difference between a DSIC constraint and a BIC constraint. So remember, when there's other people, there's a distinction between saying my action is best for me, no matter what other people are doing, versus it's best for me on average over what people are doing, okay? Given some prior over what they're doing. Okay? So we're going to be talking about Bayesian incentive compatible mechanisms, okay? Although this linear program could encode each. But so what would be the BIC constraints? So now you want to say, well, for every bidder I, given the information it has when it chooses an action, when it's choosing whether or not to reveal directly or not, and so what does it know? Pretty much all it knows is its valuation VI. It does not know that of the others. It's pondering some misreport, VI prime. And direct revelation should be best for it in the sense that it should maximize its expected utility. Okay, so averaging over V minus I. Okay. So this is going to be the average. So this is just the possible values by the other bidders. This is just my notation for the probability that the other bidders have this V minus I. I'm writing this assuming that the different F sub i's are independent. Otherwise, I would just want a condition on V sub I here. It would be the same thing. And then I just look at, for this particular V minus I, what is in fact the utility of bidder I. Okay, so sum over J and U, Vij, Xij, V bar minus Pi V bar. And this should be at least the analogous expected utility for the misreport Vi prime. Okay. So that, pretty much by definition, are the Bayesian incentive compatibility constraints. Okay? You could equally well encode DSIC if you wanted to, then instead of having the sum over all of the V minus i's and a constraint for each VI, you would have a constraint for each VI, V prime I, and V minus I. And then the constraint would just be that this is at least this. Okay. All right, so similarly, so Bayesian individual rationality, same thing. So for all I and truthful reports VI, averaging over the possible types of the others, it should be that the expected utility of truth-telling is non-negative. Okay? And then it's also important that each good is sold to only one person. So sum over I equal 1 to n xij v bar, most 1 for all j, for all v, and then non-negativity. Okay. So that's how you'd write down the analog of this linear program. Again, solving for the revenue optimal BIC mechanism as the solution to a linear program. Okay? So just like before, there's a correspondence between the feasible solutions of this polytope and the mechanisms, the direct revelation mechanisms that satisfy Bayesian incentive compatibility and individual rationality. Again, you can just read off from a solution to this linear program, what is the allocation rule, what is the payment rule. And again, because valuations are additive and betas are risk neutral, you can just handle each item j separately, and you can just do, for example, randomized rounding. Okay, so if you solve this LP, you would look at a given j, look at the xij's correspond on a given input valuation profile v, and you could interpret those as the probability that each bit or I gets that item j. You could just flip coins and allocate correspondingly. Okay, so any feasible solution to this linear program can be realized as an incentive compatible mechanism. So what I want to leave you with is the following observation, or the following issue. So when we had a single buyer, and we talked about the size of this linear program, we said that it scales linearly, or it scales polynomially with the number of possible valuations of this one buyer. Okay? So certainly in our simple examples, right, that was like 2 or 3. Okay, we just have these small discrete distributions. So as long as the support is reasonable size, this linear program is reasonable size. So how many decision variables are there in this linear program? What is it proportional to? What if there are n players and each has a support size of cardinality 2? How many variables are there in that linear program? So there's n players, right? And this v arrow is an n vector, right? Where each entry can take on any one of that bit or i's possible valuations. So even if you only have 2 different possible valuations, there's 2 to the n of the strategy profiles. And probably you have many more than just 2 valuations, okay? So here, for the single buyer case, the number of variables was, you could imagine scenarios where this would be reasonable size. Basically, you cannot even imagine scenarios with any reasonable number of players where this has reasonable size. Okay. Yeah.
We only need to do this linear thing once, right, to find the mechanism.
That's true.
Yeah.
So like if you could write this down, so you're absolutely right. So like you'd potentially be happy if you could solve this with 2 weeks on a huge cluster. I claim there are plenty of problems where you can't even fit this into the memory of all the world's computers. So, but yeah, you raise a good point, actually. Excellent point. Then it would just be sort of table lookup to figure out what to do once you solved it. Yeah, Ollie.
The constraints, though, how many constraints are there?
Wow, okay, good.
I don't think it's not exponential in the constraints.
Well, unfortunately, there's this one.
Oh, is that?
So this one says that goods can only be sold once. Still, I mean, you're totally on the right track. So for the IC constraints, it is a reasonable number of constraints, and the IR constraints is a reasonable number of constraints. And we're going to leverage that at the beginning of next lecture. Okay? So excellent point. So there seem to be some opportunities for compression, or for optimization. Okay? But I just want to point out that we need to do something. So exponential size in n. And it's in 2 senses. I mean, in these lectures, I'm not going to emphasize the computational aspects. I'm not going to necessarily envision actually solving these linear programs. I more want to get a conceptual understanding of optimal mechanisms and what they look like. And even for just that conceptual understanding, this is the wrong linear program. Okay, it's just sort of a too wasteful encoding of the optimization problem. So this is too big. We want to do dimensionality reduction, and that's going to be the main topic of next week. So see you then.